wanted to make a brief comments that or announcement that I just mentioned. So one, in the past we always printed out lecture notes and had them available, but it seems kind of quite expensive, both financially and in terms of burning paper, and and especially with updates of the lectures, we decided this year to try to simply have it available online. So just for your reference, everything's on the website, and we post them as fast as the lectures to give us the lecture. And then we'll get updated as the typos get caught or you catch typos. So that's one comment, and I hope that's okay. If you really, for some reason, really don't like that, you can approach us and you can fix your personal copy. But hopefully for most of you, electronic version will be sufficient. You can also annotate in PDF. Second comment is I misstated the login, user login name. The password was correct, but the login name I said it's matter, it had C dash in front of it, so it's C dash matter.
C dash, not underscore.
Right, C dash matter.
Oh, it didn't work for me. Is that sure?
Well,
I tried that this morning.
Did you try C dash matter?
Yeah, I did, because it was on the board when I first got here.
Okay.
Did anyone get it to work?
Did anybody get any username to work? Did you?
I think if they tried the matches matter, it also worked. I never got it.
Did anybody get username to work? Problem is I can't check it because I try to check it, but the system already knows me, so you won't accept anything. You
have a bad reputation.
Yeah, exactly. I'm a known item here. So it's hard for me. It's hard for a local person to check this username. So Shao, did you check it and you checked? You just checked it and not?
Yeah, computer.
And you used C dash matter.
Yeah.
Okay. There it is. So I'm amazed actually that nobody's. Has anybody logged in?
I did.
It didn't work. I feel. Okay. We'll have to check on that. Okay. But you can for now use user. Yeah, guest user. Okay, so without further ado, we have Alex Levine, who is from UCLA.
Okay.
I won't give extended introduction.
Okay. I am Alex from UCLA, and that is a full introduction. So what I'd like to tell you about is, I guess, in a sense, moving on in continuing the theme we already started this morning, is using elasticity theory. And fortunately, Tom presented a very elegant view of the subject from the step 0. I'm going to try to jump in looking at linearized elasticity theory to apply it to filaments and membranes. You might ask, why would you do this? One way I think about it is that elasticity theory does a nice job of eliminating the need for looking at atomic coordinates. It packages all these sort of atomic interactions and coordinates into just a couple of numbers. So Tom introduced the elastic constant tensor, and if you go to a isotropic system, you reduce that to actually 2 Lemay coefficients. And the beauty part there is that all the details that you might worry about have been subsumed into 2 numbers that are at least experimentally measurable, even if you don't wish to compute them directly from atomic or molecular interactions. And in a sense, if you're studying things like actin networks or lipid bilayers, it's somehow not only more complex, but fundamentally inelegant to ask where all the atoms are. It'd be a little bit like taking your car to the shop, and the mechanic says, "That's all right, Alex, I have all the atomic coordinates of your car from the last visit, and we'll just compare to figure out what's wrong with it this time." You can imagine that's a poor way to think about the car or anything else. The advantage of this picture for elasticity theory can be, in a sense, continued by using geometry. The thing that this makes filaments and membranes distinct from the sort of picture that Tom started discussing with you is the idea that we have either 1 or 2 small dimensions compared to the others. And by using the fact that the deformation is simple in the small cross-section, we can develop an even simpler theory for thinking about filaments and membranes with even a more restricted set of experimental parameters. So, for instance, if you look at a filament, the basic idea is that I have some sort of object that has a cross-sectional thickness with a characteristic radius, say A, but I'm interested in a piece of it, L, that's very long compared to A. And if I have a membrane, I have one thin dimension. I have a thickness T. So if I have a shell or a membrane, I have T within, and I have an area A, and I'm going to count on the fact that T is always much, much less than the square root of A when I think about this problem. So, of course, a piece of paper does a pretty good job of being in this limit, as you can see. I guess because my brain falls into the same pathway each time, I included in my notes pictures of actin networks. It's not worth pulling up the computer because you'll have them. They are the characteristic green liney bits that are inside cells. You will see them. And my point is that you don't really want to know where all the atoms are inside one monomer of actin if you want to think about the problem on the scale of microns. And fortunately, elasticity theory of filaments and membranes allows us to make the conceptual leap from atoms to extended objects where we characterize them by a deformation field. So, just to give you a slightly more concrete outline of where I'm going, what I'd like to do is the following. Let me see if I can lift this up. I have to say this is one of the few times when the blackboard is actually low even for my height challenge sense. So I will move it up to here. I feel very tall for the first time for the first time. So I'm going to start by talking about filaments. The basic outline of all of these discussions will be we're going to start from mechanics, and then if you like, graduate to statistical mechanics. We're going to develop a mechanical theory of a rod. We're going to include torsion, so we can take our rod and we can twist it. We can include bending. You can take that rod and you can bend it. And in fact, you can then worry about the full, if you like, T equals 0 mechanics of that problem. And in fact, we'll see that if you take a rod with sort of a funny cross-sectional shape, you can't avoid mixing torsion and bending. And if you don't believe me, you can take off your belt and try it. And I will give you, I brought a belt. I'm not wearing it now because I didn't think ahead, apparently. But I will show you next time I give a lecture on that one. The next step will be turning this into the statistical mechanics of a filament. Oh, by the way, please do interrupt me and raise questions. Just yell out my name or vice versa, or just say, I have a question. Otherwise, I love hearing myself talk, so I'll be here all day. So what we're going to talk about there is we're going to ask, well, if you now have a thermalized filament, you can ask questions about the statistical correlations of, say, the tangent vectors at one point and another point. You can ask questions about the typical end-to-end distance and how that changes with the stiffness or the mechanics of the filament, and we'll try to understand how that works. In fact, these kinds of ideas underlie most of the thinking in biopolymers. People talk about those correlation lengths rather than mechanics typically, and we'll see why. I'm going to then move on to the small bending limit and stiff chains, or stiff filaments. So we can talk about semi-flexible networks. At this point, you might be wondering, what does the word semi or the prefix semi have to do with this? And I'll try to define that as we move on. And as a final point, I'd like to talk about when the idea of this sort of packaging of small distance information being subsumed into experimentally measurable constants in a larger length scale theory fails. So this sort of packaging of short distance information breaks down when you strain a system sufficiently that the energy all of a sudden becomes concentrated in small regions. If you take a drinking straw, you can try bending it until finally you get this sort of catastrophic kink, and then it's not a good drinking straw anymore. So don't try it during lunch, I guess. You can also see the same thing, in fact, with bending short pieces of DNA. And I'd like to tell you about an experiment on pulling proteins with DNA, where this, in fact, came up. The experiments have nothing to do with me, in fact, but my colleague Giovanni Zocchi at UCLA figured out a way of gluing very short pieces of DNA to a single protein and using the DNA as the bow, as in like an archery bow, where the protein is the tensed bowstring. And by doing that, by pulling on proteins in different directions, looking at how that changes their biochemical activity. Along the way, we learned that you can also kink DNA if you pull too hard. And I think it's a nice demonstration of some of these ideas put together. So that's the outline of filaments. And if I don't wear out my welcome, I'll tell you about membranes on the next one. So that's where I'm planning to head. Let's start with step 1 here, the mechanics of rods. In some sense, torsion is easier to think about than bending, I think. So it's probably a good place to start. So what I really mean by torsion is I'm going to imagine I have a rod. At this point, I draw rods as if they have a somewhat circular cross-section, but I'm not obligated to believe that at this point. So you could imagine that the cross-section of this rod is actually the profile of Abraham Lincoln at this point. If you choose, it just would be harder to do the math. What I really want to do is I want to imagine that I have some radius r here. And what I'm going to do to my rod is I'm going to apply a twist so that my axis of rotation is collinear with the long axis of the rod. So I'll be twisting it about that axis. Although if you believe in the right-hand rule, as I guess I should, I'm twisting it about that axis, if you prefer. So what does that really mean? It means that as I move down the rod in the z direction, each cross-section of the rod has to rotate relative to the one before it. So in other words, if I drew some crosshairs on the z equals 0 cross-section, and now I move forward to the z equals epsilon. By the way, if I sort of run out of real estate here, can you see me? I think only the people in the back. It's okay, I see a thumbs up. Okay. So what that means is that in the next cross-section, those same crosshairs would now have been rotated by a small angle. And I'm going to define that rotation in terms of a derivative, or tau, a rotation angle. So in other words, I could imagine a function phi of z telling me the twist as I wander down this rod. Okay? Good. There's only 2 boards here, right? There's 3? That I think. Oh, okay. I hadn't hit bedrock yet. Fair enough. Well, you know, yeah, that's true. I guess I should. Years ago, when I was a beginning TA, they taught me blackboard management, which meant start here and end up there. It took them 2 hours to teach me this, and I think I probably needed a 3rd hour. So, sorry about that. So to stay in the linear elasticity regime, I'm going to assume that displacements are always going to be small. The mapping from the reference space to the target space is always going to be a small distinction for me. Now that's going to be okay because it means locally in each slice things are moving a little bit, but remember that can add up, so I can actually take a stick or a filament and twist it all over in space. I just can't do a lot on the scale of the cross-section if I want to stay within the linear elastic regime. So I guess I will do this. So how do points move under torsion? Remember, if I want to connect to elasticity theory, the first thing I'm going to need to do is figure out what are the displacements, what are the strains, and from that I should be able to compute the elastic energy associated with a particular deformation, following Tom's lecture. So,
tau is a twist displacement?
yeah, that's right.
Or twist strain. Twist strain.
Yeah.
Such that when I multiply by epsilon.
Yeah.
Thank you.
Sorry, okay. Yeah. So phi is the angle. This is the angle through which I'm twisting per unit length that I walk down the thing. Okay. So, in fact, I think I'll come to it right now. Points in a cross section in fact, exactly have to rotate. So this is my little change in position. And from that, I can compute the displacement directly. The displacement of points in the x direction is simply taking this result, saying that I'm going to write this in terms of, I'm going to write my delta my delta phi as d phi dz, or tau, times a little dz, or an epsilon. I can integrate that up and end up with my displacements in the x and y direction, which are prescribed, actually, by what I meant by torsion. Notice I'm not done, though, because I still have the z direction. There's nothing obligating the system to stay planar in the z direction at this point. So I have to ask myself, what does the z displacement of each little slice look like? So first of all, each little cross-section is turning, but it's also perhaps warping in and out of the z direction. That's what I need to think about.
How is it constant?
Yeah, well, it's going to be, yeah, so that's what I took it to be right now. Yeah, that's right. Locally, I can do that. And then we can decide what to do if we decide to make it vary along z in a minute. That's a good point, and I should have said that. So you can see really all I'm doing is saying that I have an unknown function of the cross-section. Because it's linear, I'm assuming all these terms are in the linear response regime. I can say that whatever my uz displacement is at some function times the amount of twist I put onto it. So now I've actually used up my real estate properly. Let me, well, I will leave this one alone. Go over here. And if you follow the words of Landau and Lifshitz, that's the function psi they call a torsion function. Now we can actually do what we need to do to calculate the strain tensor.
Might not want to write the shadow.
Oh, yes. Something I should have learned from the previous lecture, yes.
There's different, this is a tiny point, but there's a different signs on the UX and UI.
There are. And did I? Oh, I have the same sign on them. Just so I get my notation correct. UX and UI. Yeah, it's a cross product after all. So sorry about that. Okay, so. Yeah. There we go. So using the linearized strain tensor, we can see immediately that uxx, uyy, uzz all equal 0. So independent of the material, whether it is incompressible or compressible, a pure torsion does not change the volume within linear elasticity theory. You'll also see that xy equals 0. We're left with, though, two shear terms, which are both proportional to the amount of twist you're putting on the system. and can be written in terms of this torsion function, like so. So from this, we can calculate the stresses. I don't think that Tom wrote the stress-strain relation in precisely this form. So just to define my notation, at least, let me write it for you. There's a number of different ways to write down two numbers. You can write down the two Lemay coefficients, as Tom did, and of course that's perfectly valid. You can write things down in terms of a shear and a bulk modulus. You can also write things down in terms of a Poisson ratio, which is a dimensionless quantity, telling you how compressible the material actually is. As nu approaches 1/2, the material becomes perfectly incompressible, and this mu is the shear modulus. So if I'm going to use this notation only because I have it in my notes, and if I try to swap it back and forth, I will just make a mess of it. So.
Can I ask, just to make sure I'm clear on geometry?
Yeah.
These U's are deviations from what reference state? I mean,
from the untwisted reference state of.
You're allowed, the filament is allowed to bend away from the axis. Are you just talking about?
I'm doing a pure torsion. So what I'm allowed to do is, like, let's say this is a cross section of my filament. I have prescribed a certain twist to it.
Right.
And now what I'm saying is that this is allowed to move in the z direction in principle. And in fact, in practice, it will.
Okay, but it's not allowed to actually.
No, there's
non-trivial.
No, not yet.
Like a telephone, okay.
No, you're not going to produce a telephone cord by twisting at this point. I've made, so far the assumption I've made is that it is linear in the amount of twist I've done. Well, yeah, so that's because each slice is going to move forward or backward in the same way. Let's see if we can find a solution that looks like this, and then we'll decide what we think about it. Okay? Well, so you would imagine if I twist this about the central axis, this point has no x or y displacement. In principle, it can move in the z direction. We're going to try to answer that question right now. Okay? So how do we answer the question is we're going to have to insist on static equilibrium. Yeah, sure. Yeah, so you'll notice this is, in fact, telling me about the volume change. So this has to somehow relate to the bulk modulus. Okay. Yes?
Is this strictly true for solid rods, or if we have hollow rods?
If you have hollow rods, you're still going to be fine. In fact, we can talk about the difference later on. What I hope to do is subsume all the details of the geometry of the cross-section into one number, which is going to be a torsion modulus. And that number, of course, will be related to some sort of integral over the slice. And if the slice has holes in it, you don't get to integrate in the holes. So we'll come to that. But yes, that's in fact a good point. So I draw them like this only because my artistic skills are hit about that limit. So, but later, in fact, it'll be nice to have circular cross-sections for simplicity. So our next point is we recall from the previous lecture that static equilibrium requires all of the gradients of the stress tensor to be 0. And fortunately, from a combination of the strain tensor we've computed up to an unknown function here, we can now appeal to static equilibrium to try to tell us something about what this torsion function actually looks like.
Things with linear order, so it doesn't, these distinctions that Tom
Yeah, exactly.
do not matter.
That's right. So my stress tensor, I think as Tom pointed out quite well, all of the stress tensors become the stress tensor if you stay in linear order. Or, is that clear? Yeah, good. Okay, let me, what do I do? I actually want to keep this down for right now, so I'm going to move over to here. And keep going. Okay. The piece that actually matters is the part where beta equals z. And if we look at that term, we have just two pieces. Why? Because sigma zz has already been determined to be 0 to begin with. So what we find actually is that this requires, and I'll let you work out a little bit of the details here, that the Laplacian of the torsion function must vanish in order to have static equilibrium. So, and what I mean by, I'm sorry, you're going to ask me what this means? Oh, you're right. There we go. And no, I have it right in my notes. Boy, if I actually just could, do the reading comprehension part, I would have been fine. Okay. And what I mean by this is the Laplacian like so in the xy plane. Now, actually, I can define a new stress function, which will be chi, such that why am I doing this? The reason is that I actually can take care of the Laplacian condition automatically if I define such a function with a minus sign here. And now I have an advantage. This becomes simply a matter of keeping track of that minus sign, and we've actually managed to save ourselves a little bit of work. Now, in this new language, though, we find that the Laplacian of chi is a constant, but is in fact -1. We need to solve that differential equation to complete our job. And to do that, we're going to need to say something about the boundary conditions. To think about the boundary conditions, let's go back to our oh, this is 2 mu tau. Mu. Sorry, you're, well, yeah. Okay, well, sure. I'll try to write bigger. Sorry. Let's see, what boundary conditions? So let's think about the boundary conditions a little bit more. Here is a piece of our filament. If I imagine a little patch of surface here with a unit normal n hat, like so, and again, this is my z-axis running down the center of the filament, I'm going to consider the case where I have no applied stresses here. I'm not grabbing the outside of the filament. I'm not torquing it here. So in fact, as we talked about in the first lecture, the force applied to this little patch by the outside world is 0, which forces me to say that the stress tensor components must add up to vanish on the boundary as so. So for instance, sigma xz n hat, sigma zy n hat y vanishes. What you can do is you can see from these equations that this tells me that the following is true, and I think I need a bigger chalk. Oh, that's what I wanted. Thanks. All right. This actually is a simple geometric interpretation that's nice to look at. So let me lift the board a little bit. If we look at the cross-section, or a piece of the cross-section of the rod, so now the z-axis is coming out at you. Whoops. Think about the rod poking out towards you right now. Let's say the boundary curve of the outside looks like that. Then, in fact, the boundary we can write in terms of an arc length, L, along the boundary like so. Then, in fact, we have a local tangent vector along the boundary like so. That's simply the derivatives of x and y with respect to the arc length variable. So you can think of this as the rate of change of a point moving with unit speed along the boundary. If Yeah, you're right. Not that it gets me out of trouble, but I again need to follow my own notes. So thank you. That, in fact, is necessary. Otherwise, I'm going to have trouble in a minute. The local outward normal here, let me write it. I can write that as y prime minus x prime. And you can see that, in fact, it's the normal to the tangent because the dot product of these two is obviously 0. And if I've chosen my signs correctly, it's the one here that pokes outward when you traverse the curve in this direction. So if you write things like so, sure, sorry. So what I've done is I've defined a local coordinate frame that's moving along the boundary of the rod. So again, the rod is coming out directly towards you. You see some sort of cross-section. And now I have an arc length variable L, which is traversing the boundary curve of this rod. So out here is air, inside here is rod. And I've written down a point on that boundary. The derivative of that point with respect to the arc length is the local tangent vector. So it's the unit velocity point moving along here. And if I simply swap the two pieces of the vector and put in a minus sign, I get a normal to that vector. And if I choose the minus sign on the right one, I can make it the outward normal. Okay, so that's a lot of words for a very simple thing, actually. But that's too many words. So what that means, actually, is that my condition up here, which I'll, just for completeness sake, copy, translates into the following statement. I just realized I'm in the shadow again. Let me do that. Translates into the following picture. And notice what this is. This is simply the total differential of chi as I move around the boundary. You see that? And we know that, in fact, that's 0. So what we've just learned is that on the boundary, d chi vanishes. So in fact, our stress-free boundary condition in terms of this new chi function is simply telling me that chi is a constant on the boundary. Now, someone asked me about putting holes in the inside and so on. Chi is also going to be, for the same reason, a constant on in the interior boundary, just the constant may not have the same value. So that's the big trick. I'm not going, in my notes I did a hole case, but I think I'm just going to do the one without a hole. I'm talking to this vague area over here because I don't remember who asked the question, to be honest. Am I even on the right half of the room? No? Yes? Oh, thank God you're there. Good. Okay. So what we've just learned is chi equals constant on boundary. That's actually a big help for us because that gives us a chance now to solve the appropriate differential equation to figure out chi. What good is all that? You say, wow, well, so far you've watched Alex work up a sweat, but now what's the answer and what does it mean? Well, what did we really want to know? What I really wanted to do is I wanted to calculate the elastic energy stored in each little slice as I go, due to the fact that I did some work to deform the material in order to twist it. If I know that, I'll know the elastic energy that I put into torsion, and from that I should be able to write down an elastic free energy in the same way Tom did for not for a 3D bulk solid, but for the particular case of twisting this thin rod. And in fact, we're almost there. What we have is can chi vary in z? I'm only going to look at one little slice. So I can, in fact, yes, chi, in principle, I could imagine a system that has a different amount of twist as I go. In fact, I can prescribe any twist trajectory in the world I choose and tell you what the energy is when I'm done, is the plan. So, and the way I'm going to get that is to get the elastic energy. I'm again going to follow what we heard this morning and say, I think the notation was FEL. Yeah, I'll try to keep all that the same. Or elastic, I would have thought, but what do I know? Well, I'm going to have to integrate over, as we saw earlier. Now, of course, we had a big discussion this morning about which stress tensor really goes here. And the beauty of linear elasticity theory is you never have to say you're sorry for just writing sigma and moving on. So I'm not going to have to bring that up now. Of course, you miss out on all the interesting physics that happens when you go beyond linear elasticity, but it allows us to look at a particular problem. So, and this, of course, is integrated over a two-dimensional cross-section of the reference state, because what I'm doing is I'm actually computing the elastic energy per unit length, per unit delta dz as I go. Yeah?
Sorry to go back.
No, go back.
I realize that I'm not following. You know, when you introduce pi, you solve that condition of the divergence of sigma equals to 0.
Yeah.
And so it automatically solves it.
Yeah.
Then what is this equation you wrote down? Laplacian, perpendicular Laplacian of pi equals to -1.
Yeah, that takes a little bit of algebra, but in fact works out.
But what is that? Is that an additional condition?
No, that's a consequence of what's already there. It's not obvious. It's on page 3 of the notes, and it's literally just algebra.
Once I have that form of
Yeah.
Once you introduce pi.
Yeah.
I still need to solve that equation. Pi is not free.
That's right. You still have.
I guess it's because the curl of sigma x I z is 0.
Curls.
-1.
Yes.
There's some condition on the curl.
That's right. There's a condition back on. Yeah, exactly. What happens is the equality of the mixed partial derivatives of psi gives that to you. Yeah, exactly. I didn't want to. I thought I had beaten the algebra to death, and I wasn't going to do that piece. But everything, it's not that I'm creating this out of whole cloth. It's actually in the paper, and you'll have it later today. But if Leo asks a question like that, maybe you have the same question, you should ask me, and I'm happy to sweat a little bit more and put down the whole equation. Okay?
Well, I mean, the algebra is not important. It's just that's a separate condition.
No, that's right. Yeah. There's no. This comes out from the math, is what I'm saying. There's no additional rules. So when we get to here, though, the nice thing is that we've eliminated most of the terms in the strain tensor. So in fact, there's very little left to compute. It turns out that, again, this is a couple of algebraic steps removed from being completely obvious. You can write things like so. Notice I have a linear relationship between strain and stress, so I can also write the elastic energy density as a quadratic form in terms of sigma alone. And when I do that, the elastic constants end up in the denominator, just by dimensional analysis. In terms of my new chi function, this actually is particularly simple. Of course, now the energy is proportional to the torsion squared, the twist angle squared. And that makes sense because it had better be true that if I take z to minus z and flip my angles from positive twists to negative twists, I get the same energy. So, and what's left is the square of the two-dimensional gradient of chi, which now can be, of course, computed. Yes. So, sorry. Good point. I was so eager to get back to the other side of the room, I stopped integrating. So, all right. So, I think it's worth doing this at least once. One of the, as you saw, I think Tom pointed this out too, one of the great tricks of elasticity theory is getting to integrate by parts, which really just takes interior things and puts them on the surface. And of course, because the interior bits of the material have to support the forces from their neighbors, forces have to get, in the end, transmitted to the boundaries. And that's really that's the physical interpretation I can give you for why you can turn these things into boundary terms. And the reason we want to turn this into boundaries, into something related to the boundary, is notice that chi is particularly friendly for us on the boundary. It's in fact a constant. Yeah, it allows us to, in the end, put all the problem onto the boundary, as I think the right way to say it. So, in fact,
Fair to say that psi, as
yeah.
you work exclusively with psi, would have a much more complicated boundary conditions than psi.
That's right.
Virtue of a very simple boundary.
Exactly. There's no added information in going to this auxiliary function. It's not that I've added new physical insight to the problem, but I've written the problem in a way that allows me to put it onto the boundary. I think that I'm just saying what you're saying, I think, actually. So.
But I mean, chi also solves explicitly. Introducing chi allows you to solve stress-free condition.
Yeah, it does. Right. But remember, the divergence of sigma is exactly the thing that allows me to move interior things to the boundary. So I will just write this out because it's worth seeing at least once, I guess. I can write this. Integrating by parts means I could take the divergence of chi grad chi. And of course, when I do this, I get what I want, but I also get something I don't want, and I'll subtract off the piece I don't want. And the piece I don't want is particularly simple, because this to minus 1. By the way, when I want to exclaim, I do this. When I want factorial, I do that, just so you know. I'm just being excited, not trying to tell you it's minus 1 factorial. That, oh, yes. Thank you. They're all perpendicular in this problem. Yes, good point. So the net effect of this is that, sure. Oh yeah, so yeah, so I probably didn't give you the sort of strategic overview is the problem. What I'm trying to do is I want to say, when I twist a rod, I want to write down an elastic energy. I don't want to have to go through this rigmarole of keeping track of the internal displacements in each cross-section. I want to figure out how to integrate those out so I have an effective theory for my rod that doesn't need to keep looking inside the rod to see what's going on. So the picture I have is that in the same way elasticity theory packages molecular and atomic interactions into a couple of numbers, by making the rod thin in two directions and long in one direction, I want to package some of all those elastic constants into one new effective number that tells me how hard is it to twist the rod, and I don't have to go open up the box anymore. So at some point, you may say there are situations where you do have to open up the box again, and I'll try to point out why. But the whole purpose of this calculation is to hide all of the details into one number, which we're going to call C in just a minute. You with me? Yeah. Question? Yes? The linear assumption? Oh, so what I've done is I have said that I can assume that the entire cross-section of this thing simply turns. So I've done that. I've also am assuming that even that because that I'm going through very small angles, so the actual displacements, even on the boundary, are very small. So that way I can stay within the linear elastic regime. So if I want to twist the rod, say, by 27 pi, I better go down a long distance this way, so I don't twist on one little segment a lot. Okay? Yeah. So let me write the following, in fact, in 2 steps. I'm going to say, I'm not going to call this just F elastic anymore, because I want to emphasize the fact that this is the elastic energy contribution just due to the twisting. I have a prescribed deformation to this thing. And I can write it, I claim, in terms of tau squared. And now I can integrate this thing along the length of the rod, where my constant is the piece that we're working on right now. So I probably should have said this more clearly, and thank you for the question. So here, in fact, is the program that we're trying to follow, is I'm trying to say all the complexity of the rod's internal twisting is going to be built into one number, and that one number I don't have to revisit anymore. And now I have a theory for just twisting a line, if you like. I don't need to see what's going on in there. And the whole point of the exercise here, by integrating by parts, is that I turn this into a surface term where I have the line integral around the boundary of the gradient of chi dotted into the outward facing normal. So here's my cross section. I'm integrating like that. And here's my outward facing normal, and I should get my big body out of the way so you can see what I'm drawing, but there it is. And we have one more term, which is the area integral of the cross section. The nice thing here is that, in fact, I have, first of all, I need, oh, Lord. Well, I have a minus and a minus, so I get a plus. So, because this is equal to minus 1. This is, okay, you're with me now. Okay, good. So, in fact, what I have is I have all the elastic information of the rod, including the geometry of its cross-section and whether I have holes in it or not, built into one number C. The nice thing is that because I don't care about adding or subtracting a constant to chi, I can set, if I have only one boundary, I can always choose to set chi to be whatever I want on one. I can choose it to be 0 on one of the boundaries. So the net effect is that it even makes it easier for me. So let's see where I'm at. So this, I guess this is my boundary term, like so. So with holes, you have to be a little bit more careful, but otherwise it's not so bad. This might become more simple if we look at an example. The easiest example is, of course, the one I'm going to do. Let's look at a circular cross-section. Oh my gosh. Oh, it was suggested that we take a little break at 50 minutes past. So I got about 2 minutes, and I will finish my example. And we will finish torsion, too. So after I've twisted you guys up, we will take a break, and then I'll try bending you. So we'll see how that works. So I only want to compute my chi. So what I'm looking for is if I have a circular cross-section like this with radius r, I'm going to look for a solution that's going to be rotationally symmetric, and I'm going to choose it to vanish on the boundary. So, and I need it to have a Laplacian of -1, again a 2D Laplacian. So I can choose that, and I'll put in a constant a, and if I choose a correctly, which in this case means a is a quarter, I will, R is the radial direction, and you could imagine I have an azimuthal angle, which I could call theta. So I can label every point in the cross-section by r and theta. And I'm going to choose a solution. I can find a solution that's, in fact, azimuthally symmetric. So I do that. And now the computation for C is fairly trivial, because at the end of the day, once I have chi, I've chosen things so that everything vanishes at the boundary. And I will find that C is in fact equal to numbers, the shear modulus, which sort of makes sense. In fact, there's pure shear deformation going on here. The interesting thing, in as much as there's something interesting about the answer in and of itself, is that it depends quite strongly on the radius, which makes sense after all, because the same amount of twist on a bigger circle is going to produce a lot more. Most of the deformation is living on the boundary, after all. That's where you get most of the twists going on. Near the axis, not much is happening. So in fact, you see a large power here. You can do the same thing, and you can see that if you put a hole in it, and you'll find that the torsional rigidity looks almost the same. You have to be a little bit careful. I'll tell you the answer, and I'll let you work it out. And if you have trouble, the answer's in the notes. So if you, I'll let you work it out first. How's that? You can try this one and see how it goes. See what you think of that answer. And I think you'll see it's not so bad. So we followed our program for step 1 of a rod. What I hope to have convinced you of is that we were able to take this elegant elasticity theory that we learned about in full detail and in full generality. We've reduced it to a very simple problem that lives in the small cross-section, integrated out the elastic energy across one cross-section, and in doing so, we've generated a new effective elastic constant that's built out of properties of the rod, geometric properties of the rod, and these numbers, in fact, tell you that it's circular, and one of the elastic constants. And now I don't really need to open this box again if I want to talk about twisting rods. I want to do the same thing, perhaps a little bit faster, on bending, so there's time to do more fun stuff. But that's basically the program. Yes?
So how would you define the chi here? I thought the chi should be defined from the derivative of the stress.
Yeah, so what I'm doing is I need to find a solution. Notice what all I need to do is I need to find a chi such that it has this property. And it has, yeah, and that's right. This chi, in fact, if I take that answer and plug it back through, I can go back and calculate the torsion function, as they call it, the z displacement of the filament as I go. Yeah, notice that once I prescribe the deformation, the energy knows only about the elastic constants. There has to be an energy term in here somewhere. And because it's a circular cross-section, there's only one number describing the shape, so that's the only thing that can come in. In fact, if you wanted to be, I see your question, I'll get right there. If you wanted to be somewhat bold, you could have said, this much you should have been able to determine by dimensional analysis alone. And then you worked really hard to get a pi over 2. The point to me is not to get the pi over 2, but to try to show you how the idea of the application of elasticity theory to a filament allows you to sort of package all these small-scale details into one number, yet again. Yeah, you had a question, please.
I'm curious, the plastic, that condition right there, does that also contain being constant on the surface of your filament?
No, I needed to. I had another. Yeah, I had another. We'll say, for instance, this is not a well-posed mathematical question. I need to have a boundary condition.
Right. So if you had a squiggly
Yeah.
non-circular, that would work on a part.
Yeah, exactly. And my feeling is I should start slow and taper off from there. So
I'm just making sure that that's not the only condition.
no, it can't be. In fact, I have a boundary condition as well. Otherwise, it's not a well-posed differential equation. And once I've solved it, though, you can do this. In fact, it's a fair bit of struggle to solve this if it's not azimuthally symmetric. But in a sense, I don't care so much right now. Those are numbers, and the main point I wanted to convince you of is that there is a well-defined procedure to take linear elasticity theory and use it to, in principle, develop these numbers if you need to. At worst case, you're left with a integral of something that you don't yet know, but you know it's going to, at least by dimensional analysis, have a particular form, and you could say you're working really hard to get this number, which presumably is of order unity, unless you have some very funny shape, I assume. Yeah?
So you exclude you can add a log to this, but you would be singular at the origin?
Yeah, that's right.
If you had a hole, you would have to worry about that?
Yeah, in fact, you can. If you have a hole, you have to work a little bit harder on what.
Because now you have two surfaces.
Yeah.
You still have to solve that equation, but now with two surfaces, you need that log to satisfy it.
Yeah, you need to be constant on both boundaries. It may not be the same constant, of course. In fact, typically it won't be, because the only way it could be the same constant on both boundaries would be to have chi of 0. And that's, of course, not going to be a solution there. So.
What does the psi function look like that goes with this nice chi for the solid?
That is a very good
Along the positive z-axis, or depends on the sign of tau.
It does. I think that's right. In fact, I didn't calculate that for you, but I'm going to show you when you bend something. If you paint a ring around the thing, I'll tell you how the ring deforms, how it tilts and stretches. So I wasn't going to go back and do it here, but I was going to do it for bending.
I'm not asking you to do it. I just wonder if you knew the result. Is it like a parabolic displacement along the z-axis?
I don't know the result, but it's something I can do my homework tonight. Yeah. I have my assignment.
That's a homework assignment for the class. Cool.
Oh, that's a great homework assignment. Yeah, now you have 2 assignments. There you go. So David Nelson's homework assignment is work backwards to tell me how that little cross-section is warping in the z direction. Does it look like a little lens? What does it do? So let's figure that out. So should we take a little break now? 5 minutes? Yeah. Oh, no, it's fine. I don't want to do that. Okay. Well, let's see. No, this isn't. Leah, I think this is as good as I'm going to do on the board. It's fine? Okay. Good. Okay. Well, you tell me, because it's when you're up close, it's hard to tell. Sure, yeah. I will. I can. Well, okay. All right, so let's get back, and let's put torsion aside for a minute and look at bending. It's rare in life you can say that let's start with a clean slate and actually mean it literally, but in this case I do. So we'll have a clean blackboard. Bending. So the idea is we're going to analyze bending essentially along the same lines. What we're going to do is we're going to say, take a small piece of the rod, an infinitesimal piece of the rod, force it to be in a particular bend, ask what the internal displacements and strain variables are, using linear elasticity theory, calculate the internal stresses that you've generated by doing this, calculate the work you've done in creating the bend, and then you know the energy cost per unit segment of the rod for that amount of bend. And then we can integrate that up. So the main difference here is that if you bend a rod, like so, let me look at a cross-section right through here. You see that, in fact, rather than twisting one segment relative to another, I'm actually taking material elements above some line and stretching them. So pieces here got pulled outward. On the other hand, on the inside of the bend, pieces here had to get pushed inward. So in fact, we have compression on the inner side of the curve, transitioning to stretch or tension on the outer side of the curve. Clearly, if you go from compression to tension continuously, you have to pass through zero somewhere. We're going to call that the neutral surface. Oh, here it is. Apparently, it's starting to look like just a little nest over here, so I should clean up. So here we have stretching. Here we have compression. I also have to define what I mean by the amount of bending that's happening here. I'm going to say that, in fact, locally, this little piece of rod is now being bent into the arc of a circle of radius r. So, and I'm going to say that this is the z direction. If I look at an infinitesimal slice in this little arc of a circle piece, then, in fact, in the deformed state, elements that used to be separated by dz are now separated by dz prime. And that can be written as good Lord, z, like so, where I've chosen a coordinate system so that in my slice, z points again along the axis of the rod, and now x lies in the plane of the board. So, if you recall from the morning, we looked at how little elements of oh, I thought you were signaling me to do something.
No.
Okay, that's fine. Feel free to signal me to do something, but I don't know your sign language, so.
I'll make it clear.
I'm sure you will. So we saw that, in fact, this is true. And again, if we take the linear elasticity theory, this is just the symmetrized derivatives of the displacement. So we can, in fact, compute exactly what's going on there. And we see that 2zz, and I'll leave this as a very short exercise for you, is yeah, so this is being bent into a circle of radius r. Good point. I should have put that on the board.
But it's not the bottom surface that's the radius r, it's the neutral
Let me make sure, because x is being measured from the neutral surface. So when x is equal to 0, I have no change in the radius. I have no change in the length, so I like that answer. When x is negative thickness, then in fact I'm getting a little bit of compression there. And so I think I have that right, yeah. Sure. So again, we're going to collect our solutions for the strain tensor, because from the strain tensor, using the morning's lecture, we can compute energies, and that's really where we are headed. So it turns out the easiest way to write this, in this case, is to write this not in terms of the bulk modulus and shear modulus, but in terms of the Young's modulus. So Young's modulus is named after the same Young of the double slit diffraction, who seemed to have the ability to do many, many interesting things. And you can think of it in the following sense. Imagine I take a piece of material within the linear elastic regime, and I pull on it, so I try to stretch it. But I allow the sides to be free. So imagine I have a candy bar, and I'm pulling up on it, but I'm not pushing on the sides. And I can ask the question, what's the effective spring constant of my candy bar? And that's the Young's modulus. So if you want, you can write it in terms of the quantities we already had. It's just, in fact, it's the one that's usually used for this problem. And you'll see why. What we're going to see is that bending is really nothing more than pulling and pushing. So in fact, the Young's modulus will play a big role. Now, so we've actually computed one component of the stress tensor. Couple of things to note. Let's consider this integral. What does this integral mean, actually? We talked about this sort of, well, Tom Levensky talked about this sort of thing this morning. If I integrate over the two-dimensional cross-section of my slice, if I integrate sigma zz over that, what is that actually telling me? It's the total, so this has to be the total z component of the force acting on this slice that is normal, which has a unit normal of the z-axis. So it's exactly how hard am I pulling on this side. Now, in fact, what we're going to see is that in order to bend, you're going to have to be pulling this piece out, and you're going to be pushing this piece in. But there's no net tension being applied to it. You could ask a different question, which fortunately within linear elasticity isn't any harder, which is, imagine I bend it into, like, with a form somehow into a curve, and now hang weights off the end of it. But I'm not doing that. So in fact, this integral, which is the full net force I'm applying to the side, has to integrate to 0. And because sigma zz is linear in x, it actually tells me where that neutral surface is. The coordinate system is defined in such a way that when I integrate over the slice x, I get 0. Notice this is sort of a funny way of saying if the material had a uniform mass density, I would simply be asking what's the x component of the center of mass. So in fact, people will talk about it that way, even though we'll use language, especially engineers will use that language, even though what they really mean is just this. So let's put this one up here. And now I get to clean this guy. Somehow I never got back to this board. All right, done with page 6. So Cutting to the chase just a little bit, and again, all the pieces are here, you will find that here we go. This says now all if you're having shadow-related issues. All of these terms are 0 except for just this privileged few. We saw already that uzz is not 0. Turns out that uxx is equal to uyy is equal to minus the Poisson ratio of uzz. And that's exactly what we expect for a piece of material. When I pull on it, what the Poisson ratio is telling me is how much does it suck in on the sides. I think this is also something that Tom talked about briefly. If you take a piece of material, typically you expect to see that the lateral sides squish in when I extend it to try to preserve volume effectively. And when I compress it, the lateral sides push out. And that's what the minus sign is doing there. Now, there are materials with negative Poisson ratios that actually laugh in the face of that idea. And they do so typically, in fact, I think it was Tom who taught me this years ago as a postdoc. He crumpled a piece of paper and pulled on it. You should try that yourself. I sweated over these notes, so I'm not crumpling them. But you can try it yourself. I think we've probably solved these types of differential equations enough that I'm going to skip over a little bit here and tell you that the net answer comes out to be that you can integrate these strains up to get the displacements, and it's shown in the notes. So I'm skipping a few relatively straightforward steps with calculus. You will find the following as the answer. So it should be comforting to see that this minus sign is here. You'd expect the y direction to sort of squish in for a normal positive Poisson ratio. When you're on the stretching side, when you're on the compression side, it pooches out, if that's a word. And of course, we solved this one already too. So now I think this was a question that David Nelson. I've created a linear superposition of these two over here and produced Tom's son by accident there. So sorry about that. Yeah, that's there's a whole biological question there that I don't even want to get involved in. I don't know what that meant. So what you can ask now is the question, okay, so what happened to a slice? Well, fortunately here we can actually look at a slice. So imagine the following problem. You take a piece of a circular cross-section rod, just to be simple, and now I paint a little, in this case, red stripe on it in my notes. And I can calculate what does that look like when it's bent. So just to pick numbers, I took the radius to be 1, and I took the radius of curvature of the rod to be 4 or 5, so it looks big on in Mathematica's plot. What you'll find is that you can actually look at it yourself in the notes once I put them up. You'll see that the slice actually develops a tilt to it. And you can see that because of the x-dependence, the linear x-dependence of uz. So the top part is going to go this way. Remember, we're bending in a circle this way. And the bottom part is going to go the other way. Someone asked me during the break, if you twist a rod, is it possible for the slice to tilt? And my answer was no, because how would you decide which way to tilt it? Now you can actually make a distinction between the inner side and the outer side, so it's actually possible for the rod to decide which way to go. And this is a slice that is on this side of the curve. It actually tilts over a little bit like that. And you can see why. If it tilts over a little bit like that, it's just in response to the fact that the top is getting stretched out and the bottom's getting pulled in. So each little slice gets pulled over. And of course, on the other side, when I have z negative, they have to tilt the other way, so symmetrically. And in fact, if you look at it a little bit more carefully, you can convince yourself that what started out as a circle ends up being stretched out into effectively an ellipse. So you can play with that on yourself with Mathematica or MATLAB or whatever you like, or just draw pictures. Now, we actually did things we didn't need to know for the elastic energy. What we really needed to know is we needed to know the strain tensor, and we needed to know the stress tensor, which we have, or in fact the strain tensor is enough because we can write the elastic energy in terms of quadratic terms in Uij. Nope, don't like that one. Oh, that's the other one. Okay, so now we get the bending energy. Sure.
What makes it decide to this way versus the other way?
So you get to decide because, yeah. So you remember you have an inner and outer part of the curve now. So you're curving this way. The elements of material elements on the top, on the outer side, are getting stretched out. Material elements on the inner side are getting pushed in. So now imagine you are a slice that's not directly in the center, because if you're right at z equals 0, you don't get anything. Right. So let's say you're on the positive side, just to pick one. So now you're bending this on this side. Notice what happens is the pieces on the top of your slice are getting pushed out this way, getting stretched out. The pieces on the bottom of your slice are getting pulled in, getting compressed. So your slice is actually tilted relative to its reference state.
But if they tilt the other way.
Yeah, well that happens on the other side. In fact, they do that. So imagine you drew like of my z equals 0 line. I've picked one spot and I'm expanding about a small piece here. So imagine I take.
I guess I was thinking of a ring. So
no,
you can't.
I can't. I'm only going to do this slice by slice. So imagine, so take it this way, like you cut a hot dog like this, right? I guess I'm hungry. You cut a hot dog like this, and I try to put it in a curve. That little cylinder of hot dog turns into a little wedge of hot dog like that. That's what I'm trying to say.
But somehow, if you were to make it a full ring.
Yeah, how does that?
Right? Or somehow it has to glue.
Somehow you have to fix that. That's right.
Yeah, you can't decide to the right.
Yeah, this can only be a local solution. It can't be the global solution. I'll have to think about that.
You said the local solution has an elliptical cross-section.
Yeah.
And the long axis of the ellipse is at right angles to the plane of the curvature?
Yes, that's right. Well, it depends on the sign of the Poisson ratio, actually. But yeah. Yeah, then it does. Right, because if you think about it, the stuff on the bottom's getting pushed, getting compressed, so it's trying to push out that way. And the stuff on the top is getting stretched, so it's trying to pull in. So, yeah, that's a good point. I guess I didn't make that clear. Thank you. Where was I? I was here. So now, if I want to look at a piece, the bending energy of a slice, I have exactly the same sort of calculation we did for the twisting energy of a slice. The only difference is that I have different solutions now for these pieces. So it's exactly the same work, just one more time. Notice that all of the strain pieces are proportional to 1 over r. So in fact, the answer here, the energy has to be proportional to 1 over r squared. Since these two are linearly related, I'm going to get 1 over r squared. And I'm also going to get an elastic constant somewhere. So I have 1/2 1 over r squared, which again is the radius of curvature here. I'm going to get the only elastic constant that enters the problem for me is the Young's modulus. And now I'm going to get an integral over the cross section. Like so. Now, Why is it x squared and not y squared? Well, remember, I'm bending things in the zx plane. So in fact, if I were to bend things in the zy plane, you would get exactly the same form, but you'd have a y squared here. And if you bend things in some superposition of the two, some angle in between, you can imagine it just looks worse. The point, though, is that these pieces here should remind you of something else. If you assumed that you had a uniform mass density, which you could somehow pull out of the integral then you would say this is nothing more than a piece of the moment of inertia tensor. So in fact, the way engineers typically write this is they say, the energy is the Young's modulus times the appropriate piece of the moment of inertia tensor times 1 over the radius of curvature squared. So this is the and this is the energy, or free energy, if you think about it that way, per slice. So if I want the energy of a bent rod, then in fact I have to say that this 1 over radius squared is itself dependent on where I am on this wiggly rod, and I have to integrate it all up. So I just add at that point, essentially. Notice that there is, well, let me see what I can say. Well, a couple of things, I guess. One thing you can see immediately from this answer is that if you want to be stiff with regard to bending, it's a really good idea to put most of the elastic material as far away from this neutral surface as possible. So you'll notice that when you look at a bicycle, which everyone seems to have around here, you can take a piece of aluminum, and instead of making it a solid tube of aluminum, you can take the same amount of metal and actually make it into a thin ring that's out here where all the mass is on the outside, so you maximize your flexural rigidity for the same amount of weight. And if you know what direction you think things are going to be bent in, you can even be more clever about choosing the cross section. If you want a rod that has a lot of flexural rigidity in a particular direction, you just take all the material and you move it off that direction, so it's hard to bend, which I imagine is why if you look at the way they build skyscrapers, they have these sort of eye-shaped beams. So they took most of the steel and they put it out on the outside with just a little bit in the middle. And that way, I guess you get the most rigidity for your dollar worth of steel, or weight of building, I guess, as it were. So there are a couple of other things that would be worth knowing. It's not just enough to know the energies. It would be nice to know the forces and the torques. But in the interests of time, I think I will skip over that because we'll come back to it in a different form in a minute. Let's take a look at, again, an example. Let's find out, does it? Yeah. So this and this cancel off. So I should have an energy per length. This is an energy per volume. And here I have an area. So I have an energy per length, but remember this is for per slice. I didn't write it here, but I wrote it here. So what I'm saying is that this is the energy per centimeter as you walk down this thing. And if you want the total energy, which of course has dimensions of energy, I have to do one more integral dz along the filament. And then the only trick is that I have to imagine that this is itself varying in z, so it stays inside the integral for z. But again, the picture was all of this stuff gets lumped into one number, gets lumped into this thing they call flexural rigidity, and typically is given by kappa. So you can compute. Example, let's do our friend the circular cross-section rod again, and we'll take the cross-section to be r. If you do this integral involved, you will find that Iyy is pi over 4 times r to the fourth. And again, you could have guessed the r to the fourth by dimensional analysis, and you could say, man, you worked again really hard to get yourself a pi over 4 as opposed to a pi over 2 before, but that's the breaks. Now, does this actually work? Well, there are a number of biological filaments where the bending rigidity is quite well known. So for instance, there are microtubules which have a very large bending rigidity. They're quite stiff and they're actually quite thick objects. They have a diameter of, I think, about 25 nanometers. You have filamentous actin, which you can think of as a rod having a diameter of about 7 nanometers. Given this scaling relation, you could ask yourself, oh, good Lord, you're right. There are 26 different letters, right? Seem to only use like 3 of them. Let's call the radius A. So this is 2A, this is 2A. Now, if in fact we're right, the bending modulus of a microtubule over the bending modulus of an F-actin should be something like 25 over 7 to the 4th, which of course I can do in my head by looking on my piece of paper here and getting about 163. Remarkably, that's pretty close. It turns out that the best literature values I could find put this at 176 plus or minus about 10, it looks like. In fact, it could be worse because there's apparently some controversy. Microtubules are so stiff, it's actually hard to figure out their bending modulus because in a microscope, they just look like a straight line. It's very hard to calculate, to see the wiggles on them, and people work very hard at that. So, yeah, there's an experiment where they look at thermal fluctuations. So what they do is they essentially fit them to normal modes with free boundary conditions and then back out what they'd expect wiggles to do at a point. You could imagine you could also look at correlations of 2 points, but that's apparently the data is not, maybe the data is not good enough for that, or they just didn't. And I'm blanking on the name of the authors, and I should know it, and it's just not coming to me. I'll let you know later. So, so in fact, you might say, well, this is kind of absurd because if you look at these atomic scale descriptions of what microtubules really look like, they're a big mess, and they don't really look at all like a simple rod. Same thing with F-actin. It doesn't look like a simple rod. It's actually a helical object of these monomers that themselves have complicated substructure. But the joys of elasticity theory tell you that as long as you're bending them on long wavelengths, all these sort of biological details that allow them to bind certain proteins and do things really don't tell you anything about how they bend. All you really need to know is the scaling relation, and you get a pretty close answer. So I always find it nice that I don't have to know details, and that's one case where you really don't. So let's see. Leah, what time do I quit? I think now, right? Yeah. So I wanted to finish this now, of course, but I think what I will do is just tell you that my goal is to put these two pieces together to write down the total energy of a rod with torsion and bending. From that, we're going to look at the equations of static equilibrium for what you can do to a rod. What happens when you twist it and bend it? What's the shape? And then we're going to ask what happens if you have a thermally fluctuating rod, and we're going to calculate the statistical question, which we just alluded to before. But in this case, it will be the tangent vector correlations. So that's where I'm headed. Thanks for your time.